Hello friends, today we will discuss the basic concepts of organic reactions. First thing you should remember is that you can never learn organic reactions by heart. So you should never have the opinion that each reaction is a unique one or an isolated one and each reaction you should learn it separately. No, it is never like that. So all organic reactions are interconnected. That is, you should master a few basic concepts here. Okay, now here and there, if you know a few basic concepts, then you can crack all the bones and structures in organic chemistry. Okay, now you should learn the general principles first. Now organic compounds, you have the functional groups are there. You see the functional groups are the reactant part of the molecule here. Okay, so we will be discussing it subsequently, functional groups. Then there are electron rich sites and electron poor sites, electron rich and electron deficient sites. Then we have multiple bonds, pi bonds, that is single bond, double bond, etc. Then which and the bonds which can be broken very easily. And once you get to know these fundamental concepts here, then you will have to each specific reaction you should fit into the general pattern here. So that is the way you should learn organic reactions. Correct. So now let us see. Now writing equations for organic reactions here. They are usually drawn using an arrow. So like this, these are the fundamental things I just want to, tell you that equations for organic reactions are usually drawn with a single reaction. This is called a single reaction arrow here between the static material. Here there is a static material and there is a products here. Correct. So in between there is a reaction arrow here. Okay. Now what is meant by a reagent? These are all terms which you generally use in organic chemistry very frequently here. Okay, the chemical substance with which an organic compound reacts, that is a reagent here. That is the chemical substance with which an organic compound reacts. So sometimes we can say this the reagent, we can show it on the left side of the reaction arrow or on the right or above the reaction arrow. These are the two possibilities here. Okay, now these substances are, or the reagents, are drawn on left side of the equation along with other reactants here. Okay, or it can be sometimes written, drawn, above the reaction arrow itself here. Now, when I will just show you just example when two, reactions take place here. Even sequential reactions, one reaction first and second reaction here. So this can also be shown without, without any intermediate or anything. We don't want to show any intermediate here. We can show it just above the arrow. We will be writing 1, 2 like that. So like this, we can show CH3, for example, acetone. This is your acetone here. Okay. Now acetone, the first reaction, suppose it is reacting with say reaction 1, like this we draw it, CH3MgBr, CH3MgBr, a compound here, and then subsequent hydrolysis, water. So these two sequential reactions, one after another, we can show it, the steps are usually numbered like this, one below the other here. Then we will be writing the product here. Okay, this is our product here. So this is the main product. Now, the other one we don't normally show. We are not that much concerned with this inorganic complex, whatever it is being formed here, is an inorganic byproduct. Normally we don't show. It is of not much of significance to us here. Correct. So this is the way we write here. Now, now the reagents. We were talking about reagents. So we have a compound like this. Now, this is the reagent here, bromine. That is a bromination. If you are doing it here, the products, this will be the product here. Okay, so one bromine here, one bromine here. Correct. So this can be shown like this, or this can be shown in this fashion also. There are two ways of showing this. That is, like this we show put the arrow here, bromine. On just above the arrow we write here the reagent here, then the product will be shown. So these are the simple things here, the different ways of writing the reagent. It can be on the left side or above the arrow. Now, suppose something is to be heated. What will happen? We can write here, we can write here heat, or you can just put it like this here. This is heat on above the arrow here. Now, if it is to be kept in the sunlight or a photochemical reaction, we write H nu here above the arrow here. Correct? Like this, we can show. This is the way the reactions are usually shown here. Now, we will just have a brief introduction to the organic reactions here now. That is, what are the different types of organic reactions here? That the organic molecules generally undergo, one is substitution reaction. These are the various types of reactions. Substitution reaction. Then we have addition reactions. Substitution reactions, addition reactions. Then we have elimination reactions. Then we have rearrangements. Okay, rearrangements, it will involve all these things. Addition, subtraction, elimination, and all these kind of a thing. Okay, so rearrangement reactions. So these are the various types of reactions the organic molecules generally undergo here. Okay, and in addition to that, the oxidation reduction reactions are there, acid-base reactions are there. So in addition to these reactions, organic molecules undergo these 4 different types of reactions here. Now, what is meant to be a substitution reaction? That is called a substitution reaction or displacement reaction here. Okay, it is a reaction in which an atom or a group of atoms, okay, in a molecule, it is replaced by another atom or a group of atoms here. So in a reaction of this nature here, see. So, for example, briefly, I will just give a brief introduction only. A molecule of this nature, correct? So it is reacting with Y. So what will be the kind of substitution taking place here? Correct. So here in this general substitution reaction here, Y replaces Z on a carbon atom here. Okay, the Z, it could be even a hydrogen or a hetero atom or whatever it is there. Okay, Z can be a hydrogen atom or it can be a hetero atom, whatever it is. Correct. This is substitution here. That is in a molecule CZ here, in a group here, reaction in which an atom or a group of atom, it is replaced by another atom or a group of atoms. Okay, general substitution reaction here, Y replaces Z here. Correct. Therefore, this is substitution reaction. So it all involves sigma bonds here. Important point we have to see. Substitution reactions involve sigma bonds. One sigma bond breaks and another sigma bond forms here. One bond breaking, one bond forming here. Sigma bond here. Okay. Now, example here, anything you can write here. CH3, say for example, I, methyl iodide. So this is reacting with a chloride anion here. Okay, now what will happen? So this CH3, we get Cl plus iodine. Correct. So this is the way the substitution takes place here. That is, iodine is replaced by chlorine here. Okay. So in the same way, CH3, these are all substitution reactions, COCl. Okay, plus say hydroxyl ion. What will happen? This will give you CH3, COOH here. That is, the chlorine is replaced by the OH group here. OH replaces chlorine. So this is the fundamental things about substitution. That is, all sigma bonds, single sigma bonds are involved. One sigma bond is broken, one sigma new bond is formed here. Correct. So this is substitution reaction. Now we have elimination reaction. What is meant by elimination? I will just change this page. I will briefly tell you elimination. Elimination means something is getting eliminated here. That's all. That is elimination reaction in which elements of the starting material, they are lost. Some elements are lost and a pi bond is formed here. That is, if you have a structure like this here, say C, and say Y, a system of this kind here. So we are getting a reagent. We are treating it with a reagent, whatever it is here. Okay, we get a pi bond here. That is because it is getting eliminated. See, a double bond is formed, plus we get XY. Correct. This is the elimination reaction. That is, two sigma bonds are broken here. CX bond and CY bonds here. Okay. That is elements of the starting material. It is losing here. Then a double bond, a pi bond is getting formed here. Here in this equation, here one CX bond is broken, CY bond is broken. Two bonds are broken. And a new compound XY, a new bond is formed, and a C double bond C. That is a double bond, a pi bond. It is formed here. Correct. Now, in elimination reactions here, two groups X and Y are removed here. Two groups X and Y are removed from the starting material. Now, two sigma bonds, CX bond, CY bond. Okay, they are broken. And a new pi bond, it is formed between the two adjacent atoms here. Okay, C double bond C. The most common examples of elimination reaction, we can say that when X is equal to H, these are the most common elimination reaction. X is H and Y, it is a heteroatom. That is more electronegative than carbon. Heteroatom means we have the nitrogen is there, then we have oxygen is there, fluorine is there, chlorine is there, and so many heteroatoms are here. Okay, one is more electronegative than the other. This is the most common example of a elimination reaction here. Now, let us see how the reaction proceeds here. CH3, one H here, X is H here, then we have C, say Br, so more electronegative than hydrogen and carbon atom here. Now, here this H and Br, these two elements are lost here. Okay, so this will give you, say, in presence of, say, OH minus. So what will be the nature of the compound being formed here? That is, we have CH double bond CH, then we get HBr, loss of HBr is there, correct? So this is the main compound we are getting here. This is loss of HBr. That is, these elements are lost here. Okay, then and double bond is formed here. Okay, then if you take another example, we can draw so many examples in this fashion for elimination reactions. In a cyclic ring here, we can take cyclo, say we have a OH here, 1 minute, sorry. Okay, this is cyclohexane ring. There is an OH group here, and there is a hydrogen here. Okay, now when we are treating it with the hydrochloric sulfuric acid, what will happen? The water is getting eliminated here, correct? Minus H2O. So we will be getting a product of this nature. One pi bond is formed here, double bond is formed here. Okay, plus water, whatever it is, that is a byproduct of kind of a thing. So loss of water. So this is the way elimination reactions take place here. Okay, then we have another important thing is addition reactions. The addition is reaction which elements are added to the starting material. Okay, addition reaction, new groups are added. Addition and elimination reactions are exactly opposite here. Addition and elimination reactions, they are exactly opposite. So what is addition reactions here? Addition is a reaction in which elements are added, correct, to the static material. Elements are added to the static material means this is the general reaction. We can write like this. Say pi bond is here. This is exactly opposite to the elimination reaction here. Now we are adding a reagent here, say XY, whatever it is there. So we will be getting a compound of this nature here. like this we'll be getting it here, xy. So this is adding, these x and y, they are getting added to the pi bond here. New group x and y are added to the static material. Pi bond is broken. Okay, and two new sigma bonds are formed. You see, in the opposite of elimination, that is a new pi bond is formed and two sigma bonds are broken. Here, pi bond is broken and new two sigma bonds are formed here. So, like this, if you see, say double bond here, correct? Then reaction with HBr here. Okay, what will be the nature of the product here formed? We can say C so this is an addition reaction here. Correct. In the same way here, this here, the reverse way. We can say if this pi bond, we can break this pi bond here with the water here again, hydrolysis kind of a thing, reaction here. Okay, those things we will learn in detail. It's only a brief idea I am just giving. Okay, addition and elimination reactions are exactly opposite reactions here. I will just show how it is opposite. So, like this simple way, we can just show it here. X, then we have Y. Okay, here we are adding, what will be the nature of the elimination reaction here? This is elimination, I will just show. Elimination, it will form a pi bond. Correct. Like this here. Now, this sigma bond, the pi bond is broken and sigma bonds are formed here. So this will be the addition reaction here. Okay. This is breaking a pi bond. This is addition. This is being represented here. Here it is a form a pi bond. That is minus xy. Minus xy, it is forming a pi bond is formed here. Correct? Here it is breaking a pi bond. That is plus xy. Okay, plus xy, it will break the pi bond here. So, this is the addition elimination reactions here. Correct? Elimination means minus xy, it is forming a pi bond, a double bond here. And addition reaction, xy is added, then breaking the pi bond and two new sigma bonds are formed here. Okay, so here it will be break pi bond. That is addition reaction now. Okay, now what is meant by, so we have covered substitution, addition, elimination. Then another one is the rearrangement here. So the rearrangement reaction will be interesting in the sense of, that class of organic reactions, this rearrangement means, we'll be learning it in detail later. Rearrangement reactions means is a class of organic reactions where the carbon skeleton, okay, of a molecule, it is rearranged to give a structural isomer of the original molecule. That is, we can say that suppose we have a compound of this nature here. Something like this, if you are having a compound here. So when we are, in the case of a rearrangement, what will happen? This will get shifted here. That is atom, group, ion, and all this kind of a thing. It will be getting shifted. That is rearrangement. That is the this carbon skeleton of a molecule. It is rearranged. Okay. Now here it is actually a substituent moves from one atom to another atom in the same molecule. That is, there are intermolecular, intramolecular, and all these concepts are there. Okay. Actually, the rearrangement step in such reactions, it is often followed by a further substitution reaction or an addition reaction or a elimination reaction before a stable final end product is formed. Okay, this will involve all these reactions here in the case of a rearrangement here. Correct. Now, what is meant by a reaction mechanism? Let us see. So, a chemical equation. Change this page. Because you must have often heard this word reaction mechanism. What is the mechanism of the reaction and all? Okay, a chemical equation. When you are writing a chemical equation, so it indicates the initial products and final products here. So A plus B giving C, C plus D. An equation of this nature, if you are writing here, we know only the starting material A and B and final products are C and D here. So a chemical equation, it will indicate the initial products and the final products of a reaction. Oh, it does not indicate, okay, how the reaction proceeds. That is when you see the many reactions take place via intermediates. There will be intermediates, which may or may not, it have been isolated. We don't know which are the, intermediates will be there, which we are not able to isolate here. Correct. Therefore, we do not know what is the, the step in which it is proceeding here. Okay, only the initial products we know, the final products we know. So we do not know indeed how the reaction proceeds here. Therefore, reaction mechanism means what? It is a detailed description of how the bonds are broken in a reaction and how the new bonds are formed in a reaction. Okay, when the starting materials are converted into products, how the bonds are broken, how the bonds are formed, how the rearrangement, how the shifting of one atom or ion or group from one place to another in the molecule, all these things are taking place, etc. Okay, we do not know all these kind of things. So that is the reaction mechanism here. Okay, so the reaction mechanism, it describes the relative order of reaction and rate of bond cleavage and formation. Okay, we will be knowing from the reaction mechanism, it describes the relative order and rate of bond cleavage and formation. It explains all the known facts about a reaction, correct, and accounts for all the products formed. So whatever facts we know about the reaction, it should account for the reaction mechanism. And it should account for all the products formed in the reaction here. Okay, so mechanisms means they are simply theories here. Okay, theories that have been devised to explain the facts obtained experimentally. So whatever we have seen experimentally, we'll have to explain it. Correct. So that explanation, that is actually a reaction mechanism here. Now, there are different methods we are using for reaction mechanism here. Methods used to elucidate the reaction mechanism. Briefly, I will tell you. That is, one is the kinetic studies. Okay. That is, kinetic studies means it is concerned with the rates of reaction. Okay. So this is the most general method. It is the kinetic studies here. That is, kinetic studies means it it is concerned with the rates of the chemical reactions here. So it is the most common method here. So then the second one will be, say, identification of all the products here of a reaction. Then you will be studying the reaction, changing the structure of the reactants, and you will be changing the solvent. Then whatever is the stereochemical evidences and all this kind of a thing. Okay, these are the methods generally used for studying the reaction mechanisms here. Okay, then one point of interest here will be that there is something called a principle of microscopic reversibility. Principle of microscopic reversibility. It's a very interesting word. What is meant by the principle of microscopic reversibility? That is, according to this principle, the mechanism of any reaction under a given set of conditions Okay, it is identical in microscopic details to that of the reverse reaction under the same conditions, except that the reaction proceeds in the opposite way. So we are thinking about a reverse reaction here, equilibrium kind of a reaction here, correct? So the principle of microscopic reversibility means the mechanism of any reaction under a certain condition, reaction conditions, set of reaction condition, it will be identical in microscopic detail. That means in all very minute details, it is identical to that of the reverse reaction, correct? Under the same conditions. Only thing is the reaction will proceed in the opposite direction. Okay, you can just understand, remember these words here. That is all, principle of microscopic reversibility. Then we have kinetically controlled reactions here. Okay, so when various, that is kinetically controlled reaction, kinetically controlled products, thermodynamically controlled products, so many things are there like that. You see, when various various possible products of a reaction, they are not interconvertible under the reaction conditions of the reaction conditions. That is, the various products of a reaction, they are not interconvertible. That is kinetically controlled reaction. Okay, then the product form, it will be the most rapidly formed product, will be the one that is predominant, that will be predominating in the products. Okay, that is so many products will be there. Which product will be predominating in that one? It will depend upon the speed. That is how fast that is formed. That is the most rapidly formed product will be predominating in that one. That is, various possible products are formed in a reaction. Okay, and these products are not interconvertible under the reaction conditions here. Okay, then the product formed most rapidly will be predominating in the reaction mixture of products here. They are called kinetically controlled reactions. That is, kinetic controlled reactions mean the product which is formed most rapidly, it will be predominating here. Okay, most rapidly formed product, it is known as the kinetically controlled product. That is the kinetically controlled product. Okay, then we have, if the possible products, okay, if the possible products of a reaction, they are interconvertible. Now we have seen the first thing is they are not interconvertible. Now the second one is the possible products, they are interconvertible under the reaction conditions. Okay, then the most stable product will be predominating in the final products. One is the most, the product which is formed the most rapidly, that will be predominating in the reaction products. Here, if the products of the reaction are interconvertible, that means under the reaction conditions, then the most stable product will be predominating in the final products here, provided enough time is given for the equilibrium to stabilize. It's an equilibrium reaction, so it is proceeding in the reverse direction also. So therefore, the most stable product will be predominating here. So this is known as, reactions of this type, they are called equilibrium controlled reactions. Okay, equilibrium controlled reactions or thermodynamically controlled reactions. The product formed will be thermodynamically controlled product here. Okay, the most common reactions are kinetically controlled. They are the most common thing is kinetically controlled. Reactions are the most common one. Correct. So just have an idea. Most common reactions are kinetically controlled one. Reaction rates and all. Okay, now let us see what are the important thing. So reactions can proceed. How the reactions can proceed? Okay, now a reaction can, it can proceed either in one step or in several steps. Okay, let us see how the reactions can proceed. That is, there is a possibility a reaction can occur either in one step or in a series of steps. Number of steps will be. So a one-step reaction, it is called a concerted reaction. That is, a reactant A, it is directly giving B. Okay, that is reaction proceeds without any intermediate here. That is, Most reactions are complex reactions. They will proceed via intermediates only. Mostly there will be intermediates and it will proceed via several steps here. But here, a reaction occurring in one step, it is known as a concerted reaction. So concerted reaction means the static material, it is directly converted into the product. So irrespective of how many bonds are broken or how many new bonds are formed and all, we are not concerned here. Okay, the static materials, they are directly converted into the product here. So reaction occurs, the reaction proceeds, without any formation of an intermediate here. Okay, but here generally this is not a situation here. So there will be stepwise reactions. Stepwise reaction means the A. So it will be converted into, say, some reactive intermediate. Then it will be giving a product B here. Okay, a stepwise reaction, it involves more than one step. This is known as, the first one is concerted reaction. This is a stepwise reaction. Okay, it involves more than one step. That is, the static material, it is first converted into unstable intermediates. The reactive intermediates, these are all unstable ones, highly reactive. That is why it is unstable. Okay, the moment it is formed, it is getting converted into another one. That is, the reactive intermediates are highly unstable intermediates here. Okay, these are not reactive intermediates. That is, static material, it is first converted to an unstable intermediate. It is called a reactive intermediate. What is a reactive intermediate? It is an unstable, intermediate. That is the reactive intermediate here. So which they will then undergo many reactions to give the product here. Final product will be the unstable intermediate, reactive intermediate. It will be converted into the final products here. That is the nature of the reaction here. Okay. Then let us examine the bond cleavage. This is the most important aspect here. The cleavage of the bond. What is meant by bond cleavage? That is breaking of the bond here. Okay. So now we are concerned with the covalent bonds here. Now suppose, there is a Y. It is reacting with the Rx. So this will be giving, say, YR plus X. Like this, if you know, Rx, Ry, they are all covalent molecules here. Rx, Ry. So here, Rx, Ry. Okay, these are all covalent molecules. Correct. So Rx bond is broken here, and a new bond, Ry bond is formed, or Yr bond is formed here. Correct. So the mechanism of the reaction depends upon the way in which these bonds are broken here. Okay, in a reaction of this nature, the bond cleavage here, the reaction mechanism, it will depend upon how these bonds are broken. That is, we have an Rx bond is broken here, covalent bond, and a new bond, Ry bond is formed. There is again a new covalent bond here. So what is the mechanism? It will depend upon how these bonds are formed here. So in all chemical reactions, bonds are broken, bonds are formed, you know that. Okay, now how many steps are there in the reaction? No matter. The reaction can proceed in so many different steps. No matter how many steps are there in the reaction, there are only 2 ways to break a bond, or we can say 3 ways. I will explain to you. Basically, it is 2 ways. So it can be split into 3 ways also. Okay. Now, therefore, we are not concerned with how many bonds are broken, how many bonds are formed, and all this kind of a thing. So how many ways the bonds can be broken? That is meant by, that is the bond cleavage. Okay. Now the electrons in the bond, any bond, say for example a hydrogen molecule here, say it is actually as a covalent bond here. So a hydrogen molecule, it is formed by like the sharing of these electrons here. Correct. So we get a molecule of this nature, hydrogen molecule we are getting here, HH here. There is a solid line between the two atoms. This solid line, it represents a 2 electron bond here. Okay, so 2 electron bond. One electron comes from hydrogen, one electron comes from the other hydrogen here. Okay, one s orbital here. Okay, therefore it is a 2 electron bond. Now, when the bond is broken, when we are breaking this bond, correct, this is a bond breaking here. Electrons in the bond, it can be either it can be divided equally or it can be divided unequally between the two atoms here. Okay, so between the two atoms, it can be broken equally or it can be broken unequally. These are the two possibilities here. Okay, that is why we had said, how it may proceed in many steps, 1 step, 2 step, 3 step, whatever it is there, but it can be broken in 2 ways. That is, the electrons forming the bond, it can be shared equally or shared unequally. These are the basic things here. Okay, so breaking a bond by equally dividing the electrons between the two atoms in the bond, that is known as homolytic fission or homolytic cleavage or homolysis. Okay, so the electrons in the bond, it can be divided equally, equal sharing. Bond, the electrons can be equally or unequally. It can be divided, correct? Electrons. 2 electrons are there in the bond here. These 2 electrons, either it can go with one atom or it can go with the other atom. We'll just explain now. Okay. Now, suppose we are having a bond of this nature here, A, B. So, A, B, it is a covalent bond. And this line indicates 2 electrons here. Okay, breaking a bond by equally dividing the electrons between the 2 atoms here in the bond, it is known as homolytic fission. Homolytic fission or cleavage or simply homolysis. These are the words used here. Okay, that means breaking a bond by equally dividing the electrons between the 2 atoms in the bond. Okay, so it is called homolysis or homolytic fission or homolytic cleavage here. Each atom will get 1 electron here. That is the beauty. This gives rise to free radicals. So here, in this case, electrons are equally shared here. Means we will get 1 electron here we will be getting, and this B also will be getting 1 electron here. Correct? This is the free radical. Radicals or free radicals. That is, unshared electrons are there. Free radicals, or simply we can say radical. So this is the radical mechanism, radical reaction mechanism. There are so many reactions like this which will not be going into in detail right now. Okay, so breaking a bond by equally dividing the electrons between the 2 atoms in the bond, it is known as homolytic fission or cleavage, homolytic cleavage or homolysis here. So homolysis gave rise to free radicals or radicals. So here each atom will be getting 1 electron here. Correct. Now unequal sharing, let us see. Now here it is equally given. Now breaking bond unequally dividing the electrons between the 2 atoms of the bond, it is called heterolysis. We have one is equally dividing the electron, other one is heterolysis, or we can say heterolytic cleavage, heterolytic fission, or we can say cleavage, heterolytic cleavage, and all these names are here. Okay, that is breaking a bond by unequally dividing the electrons between the 2 atoms of the bond is called heterolysis or heterolytic cleavage or heterolytic fission here. So heterolysis of a bond between 2 atoms A and B, it can give either A or B 2 electrons in the bond. Now you see, now when we have a bond like this here, so this is forming a bond like this, see, just like our hydrogen atoms we have seen now. So this is the bond is formed here, A, B, we have got a bond here. Now unequal sharing here means it is unequally dividing the electron. Here, either this can divide like this from here. This is one possibility here. And another possibility will be okay. So here, like this, it can, there can be a bond cleavage here. Okay. So what will happen in this kind of a situation? So the cleavage takes place like this. Means here actually heterolysis of the bond here, okay, between A and B. Here in the first case, A will get two electrons here. Correct. The two electrons will be with A. A will be getting these two electrons here, and B will not have anything. Okay. A will get this electron here, and B will not get anything. That is one possibility here. That is, these two will go this side. A will get these two electrons, and in this case, A will not get anything. Correct. That is another possibility. A will not get anything. B will get both the electrons here. So these are the two possibilities here. So in this type of a cleavage, we can get A, B. These are the two possibilities. Either it can be A plus so A plus B minus, or A minus B plus. These are the possibility. These electrons can be either A will be getting the two electrons and B will not get anything, or here A will not get anything, B will get both the electrons here. Correct. So when A and B have different electronegativity, if this will happen here. Okay, it will depend upon the electronegativity difference between A and B here. Electrons, normally it will be ending up on the more electron-negative atoms here. Okay, here heterolysis of the bond. This is known as heterolytic cleavage here. Of a bond between A and B, it can give either A or B, okay, the two electrons in the bond here. Therefore, A will have a negative charge, B will have a positive charge. A will have a positive charge, B will get a negative charge. Okay, therefore, this will be depending upon the electronegativity differences between the two atoms here. Okay, the more electronegative atom will get the electrons here because it will have more affinity for electrons. Okay, the attraction for electron will be more. Therefore, the bond cleavage, it will depend upon the electronegativity difference here. Correct. Here, A will get two electrons, first thing. So, and here B will get two electrons. Correct. I have just indicated here. So, this is the one kind of a cleavage here. So homolysis and heterolysis, they require energy. That is the bond breaking. Whether it is homolysis or whether it is heterolysis, this all requires energy here. Both processes, they will be generating reaction intermediates, reactive intermediates here. Okay, reactive intermediates are formed. Correct? And the products are different in each case here. Now, the homolysis will generate what is the kind of reactive intermediate homolysis? It will be giving free radicals. Homolysis gives radicals or free radicals. Okay. So homolysis generates uncharged reactive intermediates. There is no charge. There is only one electron on that. Okay. So both processes, homolysis and heterolysis, it will generate reactive intermediates. Okay. The products are different in each case. Reactive intermediates are formed here. The homolysis generates uncharged reactive intermediate with unpaired electron. Radicals are unpaired electrons here. These species with unpaired electrons, they are radicals. Homolysis generates uncharged reactive intermediates with unpaired electrons here. Heterolysis will generate charged particles, charged species, ions. We have seen that heterolysis that generates charged intermediates here. So, all these intermediates have got very short life only. If you see, each will react very quickly to form stable organic compounds here. These are all unstable products here. Correct. That is why unstable reactive intermediates here. Okay. So, free radicals, homolysis creates or generates free radicals. Radicals or free radicals, they are very odd electron molecule. Radicals, they are odd electron molecule. It is also known as odd electron molecule. That means only one electron is there. That is the unpaired electron is there. Correct. So for example, says here CH3, one electron here. That is methyl radical here. Then we can have even triphenyl methyl radical. These are all important radicals here. Triphenyl methyl radical. Okay. Methyl radical, then triphenyl methyl radical, and all these kind of things. So majority of these are electrically neutral. The free radicals are electrically neutral species. Correct. There only one electron is there. There is no charge. But however, they are paramagnetic here. All possesses, there's certain what you call magnetic properties are there. Okay, small permanent magnetic moment is there because of the presence of the unpaired electrons here. Okay, they are electrically, majority of them are all electrically neutral. Then they have addition properties. Okay, they are very, very reactive species, free radicals. They have got paramagnetic properties here. Correct. So these radicals, that is the reactive intermediate radicals, are produced during homolysis. Now, in the case of heterolysis, heterolysis will produce charged particles, that is charged ions here. Okay, this is the difference between homolysis and heterolysis here. That is, homolysis will give radicals, highly reactive intermediates with only one electron, that is unpaired electron, odd electron molecule, correct, highly reactive species, unstable. And in the case of heterolysis, it will generate charged intermediates here. Okay, so these reactive intermediates, they have got only very short life. Okay, they will immediately react, very quickly they will be reacting to form stable organic compounds. Now we have seen carbocation. Now let us see now. You see, now these different kinds of arrows, I will just explain to you. That is heterolytic bond cleavage. We have seen it involves movement of an electron pair. Okay, now A, B, this is our molecule here. Now here in the case of homolysis, what will happen? Only one electron will move. That is one electron, each atom will be getting one electron here. But in the case of heterolytic bond cleavage, it will involve the movement or displacement, we can say. Displacement of a pair of electrons. Correct? That is heterolytic bond cleavage. There will be displacement or movement of electron pairs. Okay, these displacements are represented by curved arrow notation. Again, we are back to our arrows here. Okay, curved arrows like this. That is, these kind of arrows will indicate the movement or displacement of a pair of electrons, electron pairs here. Correct. So in the heterolytic cleavage, always this movement of pairs takes place here. Okay, but in the case of a homolytic cleavage, only the difference comes. Okay, in the case of homolytic cleavage, each atom is getting only one electron. That means a 2-electron bond, when it is cleaved or broken, each atom gets one electron, means one electron only moves at a time here. That is movement of a single electron. Then we don't need a full-headed arrow like this. This is a full-headed arrow. So full-headed arrow, it is used for a pair of electrons. For the movement, so showing the movement of a pair of electrons or displacement of a pair of electrons here. But in the case of a single electron movement, the arrow need not have a full head like this. We can have a small head like this, half-headed arrow, we can call it. Like this, this is a half-headed arrow. So other one is a full-headed arrow. This is a half-headed arrow. Half-headed arrows are used for indicating the movement or displacement of a single electron, as in the case of the homolytic cleavage here. So here we can show a half-headed arrow here. One electron is moving like this and another electron is moving like this. So this is the homolysis of a bond AB. AB bond, it is homolytically broken. Homolysis. That means two half-headed arrows are used here. It will give you the product. These reactive intermediates here, A plus B. Okay, heterolysis will be different. This is a homolysis here. Okay, homolysis of AB bond. We are showing it with a half-headed arrow. That is, head is, the full-headed arrow is not there here. Only half. It indicates the movement of a single electron here. Correct. But in the case of a heterolysis, what we are doing here, it is a movement of a pair of electrons. A full-headed arrow will be used here. So it will be A plus, then we get B minus. Correct. This is a heterolytic cleavage here. One full-headed arrow, curved arrow. It is used for one electron pair. One full-headed, we can say curved arrow. These are all curved arrows. Half-headed curved arrow. Correct. So this is the thing. Now let us examine the homolysis of the bond CS bond. Okay. One bond I will just draw here, CZ bond. So the three different ways we have been telling here, it can be two different ways, but how these three different ways means, let us see. So three reactive intermediates, homolysis and heterolysis of a CZ bond, if you take it now. So a bond CZ. Okay, examples, the homolysis, how the homolysis take place here. Homolysis. So the CZ bond will be, this is our molecule. So we will be showing it with a half-headed curved arrow like this. Correct. This is the homolysis here, half-headed curved arrows here. So this will be generating the product intermediate here, we can say. See. So these are the radicals. Radicals, or we can say it is free radicals here. Now, in the case of heterolysis, how it will be? So heterolysis will be a full-headed curved arrow. We need it here. Correct. Now the bond cleavage, we will have to indicate with a full-headed curved arrow here. Okay. So the product formed will be, there is a plus charge here, then we get a minus. Ions are formed here. This is carbocation. Okay, this is known as carbocation. That is, a carbon atom with a positive charge is a carbocation here. Now, that we will be getting an ionic intermediates here. Not radical intermediates here. These are all ionic intermediates here. Okay, then these are very common polar reactions here. Okay, and another way this bond can break is, correct. So this electron pair, it will go like this here now. So we will be getting another reactive intermediate here. They are known as carbanions. Correct. These are the three different types of bond cleavages here. Okay, that is homolysis. It will generate free radicals here. That is which is indicated using, these half-headed curved arrows here. That is free radical. Each atom, it will be getting one single electrons here. Now, in the case of heterolysis, the bond can break either way depending upon the difference in electronegativities. We know that. And we'll be getting ionic intermediates here. Ionic intermediates. That is charged intermediates. ionic intermediates or charged intermediates here. So heterolysis, the electron displacement is shown with a full headed curved arrow here. So we'll be getting a carbocation. A carbocation means a positively charged carbon atom here. Correct? And in the other way, we'll be getting a negatively charged carbon atom. That is a carbanion here. Therefore, these are the two different types of things, So I will just explain it in detail. So a reactive intermediate with a single unpaired electron, it is called a radical. Single unpaired electron, it is a radical, or we call it a free radical here. Now most radicals we have seen they are highly reactive, unstable one. They contain an atom that does not have an octet of electrons. That in the case of free radicals does not have an octet. Remember that point. That is why it is very unstable here. Most radicals are highly unstable because they contain an atom that does not have an octet of electrons here. And radicals, there is no charge. They are intermediates in a group of reactions. They are known as radical reactions. There is something called radical reactions in detail. We'll have to study that. Okay, that is these are all intermediates here in radical reactions here. Now in the case of heterolysis of the CZ bond here, we have seen we can generate carbocation and a carbanion here. Okay, now here in the first case, heterolysis 1, heterolysis 2, two types of reactions we have seen here. That is 2 electrons to Z, it is given. Okay, and nothing goes to the carbon here. That is both the electrons in the bond, covalent bond, it is given to Z. And nothing is given to carbon here. 2 electrons to Z, nothing to carbon. It will generate a carbocation, positively charged carbon intermediate. Okay, it is known as a carbocation here. Now, in the second type of heterolytic fission, the 2 electrons are given to carbon and nothing to Z. Okay, it will generate a negatively charged carbon. It is known as carbanion here. So, carbocations and carbanions, they are very unstable reactive intermediates. Carbocations, carbanions are highly reactive, unstable intermediates here. Okay, now a carbocation, it contains how many electrons? A carbon atom surrounded by 6 electrons here. Okay, carbon atom containing 6 electrons. That is carbocation. Carbocation contains a carbon atom, okay, surrounded by only 6 electrons here. Correct. Then a carbanion has a negative charge on a carbon, okay, which is not a very electronegative atom here. You see, a carbon atom, it is not electronegative as compared to the heteroatoms there. Therefore, a negative charge on a less electronegative atom like carbon, it will generate an unstable species, reactive species, that is the carbanions here. So carbocations and carbanions, the carbocation has got only 6 electrons surrounding the carbon here. That is unstable here. There is no octet here. Carbocation contains carbon atom surrounded by only 6 electrons here. Free radicals, okay, free radicals do not have an octet of electrons here. They are very unstable species. Radicals, carbocations and carbanions are also very unstable reactive intermediates here. Okay, carbocation contains only carbon atom surrounded by 6 electrons. Carbanion has got a negative charge on a carbon atom. Okay, carbon is not that electronegative. Therefore, negative charge on a very less electronegative atom, it is generating a very unstable species here. Now, let us see these carbocations are electrophiles because it is a positively charged carbon here. Okay, I will change this page. So carbocations are they are all electrophiles. Electron loving species because they have got a positive charge. Carbocations has got a positively charged carbon atom there. Therefore, it loves electron to have more electrons there. They are electrophiles. Now, carbanions are nucleophiles. Carbocations are electrophiles and carbanions are nucleophiles here. Okay, they are all reactive intermediates in polar reactions. What is polar reaction? Polar reaction is nothing but reactions involving electrophiles. Reaction in which a nucleophile reacts with an electrophile. That is a polar reaction. electrophiles reacting with a nucleophile. That is polar reaction. Therefore, they are all reactive intermediates in polar reactions, carbocations and carbanions here. Okay, now let us see, we have seen that homolysis and heterolysis, they generate radicals, carbocations and carbanions in these three are carbocation, carbanions and radicals. These are the most important reactive intermediates, okay, in organic chemistry. Most important reactive intermediates are carbocations, carbanions and radicals here. Okay, so now we know radicals and carbocations are electrophiles. Carbocations are electrophiles, we know. Okay, and radicals are also electrophiles because they don't have octet. They want more electrons. Okay, they are electrophiles, radicals here. Radicals and carbocations are electrophiles since they contain an electron deficient carbon. Okay, the carbon, in the case of carbocations, the carbon is surrounded by only 6 electrons here. In the case of radical, it's only a single electron is there. Therefore, they want electrons, more electrons. They are electrophiles here. Okay, radicals and carbocations are electrophiles since they contain electron deficient carbon. Electron deficient carbon, that is why electrophile. Electron deficient carbon is there. Okay, yeah, but carbanion, they are nucleophiles here because they contain a carbon atom with a lone pair of electrons. Carbanions are nucleophiles because it contains lone pair, negatively charged carbon. A lone pair of electrons is there. Therefore, they are nucleophiles here. Okay. Therefore, now this is a brief introduction about radicals, carbocations, and carbanions here. Now, like bond cleavage, now bond formation can also occur in two different ways here. Okay, two radicals, it can donate bond cleavage and bond formation. Bond formation means it is the reverse of this one. So bond formation is say a free radical, this can, another radical here B. So how this reaction will take place here? So it can form a bond here, single electron. No? So we will indicate this like this, half-headed arrow we can show. So these two radicals can form a bond like this. In the same way, an ion, when ionic intermediates, in the case of heterolytic cleavage, we have A plus, so B minus. So the reaction can proceed in this fashion. This, it can come here. So it can form a bond AB. Correct. So these are the two ions forming a bond here. Therefore, bond formation and bond cleavage here. So before I conclude, I just want to give you a brief account of the different types of arrows. Now you must have been thoroughly confused with the different types of arrows being used in organic chemistry. Okay, now simple thing, this one, this is an arrow. This is the reaction arrow, it is called. So you should not get confused. Reaction arrow. So this reaction arrow, it is used, drawn between the starting materials and the products in an equation here. Okay, this is reaction arrow. Then we can say a double reaction arrow. One arrow like this, one arrow like this. Double, that is the equilibrium arrow. You know that. This is known as double reaction arrow. So it is also known as equilibrium arrows. Okay, these are all basic things here. Okay, that is double reaction arrow. Now there is a double-headed arrow. A double-headed arrow. This is used for the resonance. So drawn between resonance structures here. You know that. So reaction arrow, it is for drawn between the static materials and the products in an equation. Reaction, Now the double reaction arrow is an equilibrium arrow drawn between the static material and products in an equilibrium reaction. So double-headed arrow, it is a drawn between resonance structures here. Okay, then we will come to certain curved arrows. one full-headed curved arrow like this. Full-headed curved arrow. So this is used for displacement, electron displacement. Shows movement of an electron pair. Okay, now we have seen a half-headed. It's a half-headed. This is also known as fish hook arrow. Fish hook arrow. That is half-headed curved arrow. Half-headed curved arrow. It is showing the movement of a single electron. Fish hook arrow. Then there is something called a retrosynthetic arrow. Like this, we put it in organic chemistry. This is retrosynthetic arrow. Retrosynthetic means starting from the products to backwards. Okay. Then finally we have an arrow of this nature. What does it mean? No reaction arrow. Okay, these are the basic things in organic chemistry. Before we proceed to learn about organic reactions here, I just want to give a brief introduction of the various kinds of arrows being used in organic chemistry. So you should not get confused with all these arrows. Okay. So thank you very much for listening. Thank you.